Okay, so let's go on. Okay, we have now some idea of the distribution of charges. Okay, at least the positive charges that are concentrated. Okay, in a very small nucleus inside the atom. Okay, and so we will now see what about the distribution of the negative charges. Okay, so through this work of Rutherford, okay, we know that we have some distribution of positive charges concentrated in the nucleus, okay, which has dimensions of the order of 10 to the minus 15 meters, okay? And we know that the atom, okay, has dimensions are of the order of 10 to the minus meter. So there is a lot of space, okay, inside this atom. How are the charges, the negative charges, distributed in this atom? Okay, so it seems natural to assume that the electrons they are orbiting around the nucleus, okay, on some orbits. Classical mechanics, okay, allow, okay, for some stable orbits, okay, circular or elliptic ones, okay. Particularly, some of you may have already studied the gravitational centripetal force, okay, when you have some attractive force between here some mass, okay, and here, okay, the sun, for example, okay, and here you have the earth, okay, or okay, the earth, and so the earth is has some orbits, okay, an elliptical one around the sun, okay, and this orbit has constant mechanical energy, okay, k plus u is constant, okay, and so you have some force which is proportional to 1 over r to the square, okay, where r is the distance between, okay, the center of the earth and the center of the sun, okay. Here we have the Coulomb force, okay, F Coulomb, okay, also is proportional to 1 over r to the square, okay. And so these orbits are possible, okay, and we will actually the Bohr model, okay, will use this possibility of having, particularly we will study circular, this is simpler, okay, circular orbits, and this is a very classical notion, but you will use also the results from Planck, Einstein, and Rutherford, okay, Rutherford, actually this is this notion that you have the nucleus here, and you have some orbit, okay, of, this is the nucleus, and this is the electron, okay, and so the electron is orbiting around the nucleus, okay, and so let's see how we can do this description. There are some problems, but first let's see what is how we can characterize this orbit, okay. So you have a circular orbit, radius R, okay, so this is what I hide here, so R, this will be this one, okay. The distance between the nucleus and the electron. We are going to study atoms with only one electrons, okay, so you can have hydrogen atom or ionized helium, okay, or things like that, okay, one electron, okay, around the nucleus with Z, okay, nucleus, one electron, mass Me, and we have the nucleus. First we are going to fix at the origin of the, okay, frame, okay. So first we are going to, why can we say that? It is because the nucleus, particularly when you have big atoms, okay, you have a Z proton, okay, each one with a mass which is more than almost 2,000 times the mass of the electron, okay, and so you also have neutrons, okay, inside the nucleus, and so the mass of the nucleus is very, 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 okay, much larger than the mass of the electron, okay, and so we can, in the first approximation, neglect, okay, the movement of this nucleus, and we are going to say that it is fixed, okay. Something else, so we write first, this is the kinetic energy of the electron, me times the velocity of the electron, okay, square. We have the potential energy, which is of Coulombian nature, so this is minus 1/4 pi epsilon 0, the charge of the nucleus, okay, times the charge of the electron, so this is Ce square over the distance, okay, if it's a circular orbit, so this is if this is an elliptical orbit, R is not constant, okay. And so we have the total energy, E, which is the sum of the kinetic and the potential energy, okay, and this is, okay, this is this expression plus this expression. We have another expression, which is, what is the expression of the force, okay, the force that derives from this potential energy, the force centripetal, okay. This is minus du over dr, this is equal to me a, okay, so this is equal to me v squared over r, okay, and this is 1/4 pi epsilon 0, okay, Ze squared over r, okay, minus the derivative of the potential energy in relation to the distance r, okay. And so with these two expressions, okay, this is one expression, this is the acceleration, okay, in a circular uniform movement, okay, and this is the Coulombian force. And so we have a relationship between the kinetic energy here, Okay, this is not the, this is not 2, this is R. This looks like a 2. Okay, so this is the kinetic energy and this is the potential energy. Okay, so we can write it this way. E total energy is equal to, okay, minus, so we have this, what I can write here, actually, it is that, okay, I can write here that M, this is the electron, okay, I will write it M because R square, V square, sorry, V square, MV square equal to, I will call it K, okay, K is equal to K Z E square over, something missing here. This is, oh, here, sorry, this is wrong, this is right, okay? Okay, the potential energy is 1 over R and the force is 1 over R2, okay? And so mv square is equal to kZe over R, okay, because you have R here, okay? So this mv here, we will have here also minus k z capital square is equal k. Okay, this is mv, so this is minus 1/2 of mv square. Okay. Actually, you know that from gravitational force, okay, we have the same result for circular orbits, okay, of satellites, okay. So the total energy is equal to the, is negative, okay, and this is minus the kinetic energy of the satellite, okay. Okay, so we have this relation here. Let me, okay, and so what is the problem, okay, with this model? First, it doesn't explain anything, okay. So first, this is a continuum, okay. This is, we can write it also as a function of R, okay, as we have some relationship between the velocity and the radius of the orbit. So we have continuous, we can have any, okay, any value for the radius of the orbit and any energy, okay. This is what happens with gravitational satellites, okay. What is the problem of that is that this energy actually is not conserved because this particle orbiting around the nucleus is charged, and so it is accelerated, okay, centripetal acceleration, v square over r, and so as it is accelerated, okay, there will be emission, okay, radiation, okay, radiation, it will radiate an energy, radiation, okay, so you will have the energy will decrease, okay, you will have actually the radius which will decrease, and so very quickly, okay, we can measure it, but very quickly the electron will collide, okay, so you have your nucleus here, okay, and initially you have your electron, so it is orbiting, okay, and is radiating energy and approaching the nucleus and collapsing, okay, so the atom doesn't exist, okay. This is not what is observed, okay, the atoms exist, okay, and so there should be an explanation for this strange behavior, okay. So Bohr, do you remember? Einstein, he had to write some postulates, okay, to start working on his relativity theory. And so Bohr, this is what he did, okay. So collapse here. So Bohr writes two postulates. The first one, okay, this is the stationary state, okay, stationary orbit, actually, okay. So the electrons do not radiate when on a stationary orbit. So they are simply orbiting and they don't radiate, and so we don't have any of these problems. This is very, very convenient, okay, to say that, okay, we have a problem, so let's say we don't have, okay, and see what happens. The second one, okay, this is the fact that we know that atoms emit light, okay, so when do the atom emit light? Atom emits light when electron jumps from one stationary orbit to another one. Okay, and so what happens? Let me see. What happens here? So you have, when it is on a stationary orbit, it doesn't emit, it doesn't lose energy, okay? It does lose energy when it emits light, okay? But at the same time, so it goes to an orbit of smaller energy, okay? And what is the frequency of the light emitted, okay? So what is known in classical physics is that a radiating charge, okay, will emit light, okay, and if this is an oscillating charge, okay, it will emit light at the frequency of its oscillation, okay. And so here we have a frequency, the frequency of the orbit, okay. We can we can calculate some frequency of this orbit. We can calculate some frequency of this orbit, the number of cycles per second. But actually, the light emitted by the electron, by the atom, doesn't have the energy of one of the orbits, okay, what it has. So this is where Bohr uses the results of Planck and Einstein. What he writes is that the emitted photon okay, when the atom jumps from one stationary orbit to another one, the emitted photon has frequency, has energy actually. We know that it has energy. Epsilon, for example, equal to h, Planck constant, times the frequency, okay, of the light corresponding to this photon, okay. And so this energy is what? The atom loses energy when it goes from a higher energy to a lower energy orbits. So this will be the difference between the energies of the, for example, high minus low, okay, in emission. It goes from a high energy orbit to a low energy orbit. So the atom loses energy, and where does this energy go? It goes in the form of a photon which has this frequency. Okay, so it's very. We believe really that the light can be treated as particles of energy HF. So it is all coherent. Okay, so what can we do with that? What is these energies? Okay, and so he uses. Okay, Bohr uses the correspondence principle. What is this correspondence principle? This is the fact that you are using, okay, you have some very well-known phenomenon, okay, which is you have some orbit, okay, and why the charge, okay, orbiting doesn't emit, okay, this is a very restricted behavior, okay, this is restricted to small particles. But when you have, so this is the new physics, this is quantum physics. And when you have a large particle, so when you have bigger radius of orbits, you should find the same results as the classical physics, okay? So this is still valid, okay, this correspondence principles, because you can describe everything with quantum mechanics. It can be very difficult, but when you have macroscopic objects, okay, you can make some connection between the quantum theory and the classical theory as you know it, okay, the classical mechanics, okay. And so this is the correspondence principle. I will write it here in the limit of large orbits and energy. Large orbits and large energies. Quantum calculation must agree, okay, must agree with classical ones, okay, with classical calculations, okay. This is very reasonable, okay. So actually, we are not going to deduce, okay, all the results, the following results, okay, using this correspondence principle, because it's more tricky than what we are going to do now. Bohr, a few years later, he discovered that this, with this correspondence principle, it was equivalent actually to say that you had quantization of the angular momentum of the electron, okay, orbiting. So this is equivalent to quantization of angular momentum of the electron. Meaning what? Meaning that the angular momentum cannot have any value, okay? It has very well-defined values, okay? In the same way that photon doesn't have any value, okay? It has, well, the energy. You have a number, you take some energy, some light beam, okay? And the energy at each second, for example, you can measure it. It is a number, integer number of HF, okay? So this is of angular momentum of the electron. And what is this quantization? Okay, the angular momentum is equal to the linear momentum times r. Okay, it is because we have here a circular orbit. Okay, so you have the electron. Okay, so you have r, which is this way, and you have mv. Okay, and they are perpendicular. So the angular momentum, which is the vectorial product of the momentum, linear momentum and position, is equal to this one. And what Bohr said, it is that this angular momentum is equal to a number, n is 1, 2, 3, okay, times the number of the Planck constant over 2 pi, okay. And so we call it h over 2 pi is very used, okay, in quantum physics. So it has a name. This is h bar, okay. H bar is h over 2 pi, okay. And so with that, we can go on describing, okay, our system. I would like to, okay, so this is for the hydrogen atom, okay. And so what we can write is we can go back, okay, on, you remember we have, okay, L equal mvr equal n h bar, okay. And so we have m square v square r square, which is equal to n square h square, okay. Why do I square this? It is because before we have written something which is, where is it? This is it, okay. This is here, okay. mv square, okay. So I will just multiply here by m r square, and okay, I will write it here. So it is also equal to, well, I will use it here, k, okay, 1 over 4 pi epsilon 0, z e square, okay, m, the mass of the electron, over r, okay, times r square, okay, because this is m square v square, okay. And so if you write it here, you will have n square h bar square equal to k z of the nucleus nucleus times e square times the mass of the electron, okay, times the radius of r, okay, r square r, okay. And so we have, this is a number, this is a constant, this is a number, this is a number, this is a number, this is a number, this is a number. And so what we have here, this is the radius of the orbit, okay, which can be written as n square, okay, h bar square over k z e square m, okay. And so you see here n equal 1, 2. So I will call this orbit Rn, okay. So we just quantized the orbit possible, and so this is the orbit, okay, radius of stationary orbits, okay, stationary states, okay, meaning that if you have n equal to 1, 2, 3, okay, so you will have no emission, no radiation, okay, when the electron is on one of these orbits, okay. So we have quantized. Okay. And we can go on like this because for each R we have an energy, okay, so you remember we wrote that the energy was equal to minus 1/2 of mv square, and we can write it here as, let's see if I have, yes, okay, before going on here, I want to write something important, okay, we have Rn, okay, which is equal to n square, okay, and this is some constant, okay, which doesn't depend on the nucleus. So you have h bar square k and here, okay. So this is the this is a number, okay, no adimensional number, and this is also a number. So this has the dimension of the radius, okay. This is A0, this is A0, this is the Bohr radius, okay. So let me write it here. This is Rn equal to n square A0 over Z, okay. A0 Bohr radius, okay. A0 is equal to this one, we know the value, we know, and this is equal to 0.529 angstrom. Okay, this is so this is a very useful constant because you see that for a given nucleus, okay, a given Z, so you will have each time you increase the value of n by 1, okay, so you will have the first one, okay, n equal to 1 is A0 over Z. The second one is 4 A0 over Z. The next one, okay, so we can write it, we can try to draw it, okay, so this is the smallest one, okay, 1, so this is 1 R, okay, this is R1, the other one will be 4 times, okay, this radius, so 1, 2, 3, 4. I don't know if I will be able to draw, okay, it's not perfect, but okay, this would be R2, okay, and so for n equal to 1 to 3, okay, you would have 9, okay. So as you increase, okay, the quantum number, n is the quantum number, and actually it will be called the principal quantum number, okay. So as you increase n, so you increase the radius, okay, of the orbit, okay, and the, as a function it is a square, okay, function n square, okay. So what about the energy? The energy is equal to minus 1/2 of mv square, okay. So we already know that we have a function of E as a function of R. Let me write it here. It is minus half of k z e square over R, okay. This is what we already found before, okay, mv square here. Mv square is kZe square over r. Okay, so I'm writing here. And so as we have quantized orbits, so we will have, okay, and so we will have also quantized velocity, okay. And so let's see here. This is the value of the energies. So you can't have any value of the energies. You only have some values, okay. And we can write it like this: En is equal to minus. Maybe I will write it as a function of n, okay. Is equal to minus kz e square over Rn. Rn is n square, so we will have here n square a0, and here we will have z again, okay. And so we can write it, this is minus 1 over n square, okay. E0, I will call it here. Actually, I will call it E1. E1 z square, okay? It will depend. Okay, where E1 is equal, if you put n equal to 1, so it is half, okay, k e square over a naught, okay. Okay. And so what we have now, this is called the ground state. Ground state. In the book, in the Tipler book, okay, this is called E1 is called E naught, okay. I don't like okay. Okay, now I will call it E1, and this will be my ground state. You always will have to be very careful, okay, to know what is this definition. Okay, this is the ground state, the smallest energy. Okay, and for we have quantized the energy. Of the stationary states. Okay, so this is En equal to minus z square. Okay, and so as we know that the emitted photon has an energy hf equal to h. The frequency of the light is c over the wavelength is equal to E n minus em, where n is bigger, okay? This energy is higher than this one. This is positive, this is positive, okay? And so we can write it here. This is, what is En? This is minus E1 over z square, okay? Sorry. E1 z square times 1 over n square minus 1 over m square, em, okay? And so we know this one, okay? We have already seen this kind of equation. This is the Rydberg-Ritz equation. And what is the Rydberg-Ritz equation? This is 1 over lambda is equal to E 1 z square over hc 1 over n square minus this, sorry, m square minus 1 over n square, okay? And so what would be, so you can check, okay, for E1 z, okay, E1 actually, E1 over hc is the Rydberg constant for the hydrogen atom. Actually, this is not. Okay, I will call it R. Next time I will tell you the difference, because in this model we have a fixed nucleus, okay? In the experiment, okay, particularly the hydrogen atom, the nucleus is not exactly fixed, okay? So we have a two-body problem, and we have to take into account also the movement of the nucleus. But okay, so this is the Rydberg constant. Okay, so now this is not a constant found phenomenologically, okay? We have an expression for it, okay? And because E1 has some expression here, E1 equal to, okay, as a function of the elementary charge, okay, K and the Bohr radius, okay? So we are finishing. I want to come back to the spectrum of the hydrogen spectrum. Okay, so we have Z equal to 1, okay? We have 1 proton and 0 neutron. And here, well, this is 1 proton. And we have a scale in energy, in electron volts, okay? And so if you calculate E1, okay, this is equal to minus 13.60 electron volts, okay? Why is it negative? It is because the same as in gravitational, okay, description. If you have a positive energy, okay, this is a free particle, okay? And so you have these bound states, okay, they are called bound state because the orbit is located around, okay, the nucleus for negative energy, okay? This is the same thing as a satellite, okay? When you write the total energy, so it is negative is if the satellite is a satellite, if it has a closed orbit around the sun or around the earth, okay, for example, the moon or things like that, okay? So the energy is negative, it means E negative, it means that these are bound states, okay? Okay, so we can write it. This is what I called E1, okay? This is E2, this is E3, etc., etc., okay? So we can calculate them with this expression here, okay? So this is E1 over N square. You can see that the first one, this is 0, okay? So the first one is the biggest one, okay? You have all this energy. The second one will be 1/4 of this, okay? So you divide, okay? It's 1 over N square, so the half would be here, and so 1/4 is here, okay? This one will be 1 over 9. This one will be 1 over 16, and so on and so on, okay? And so we find again, you remember that the Lyman series is from m equal 1, okay? So n equal 2, 3, 4, etc., okay, to m equal 1, okay? All of them are, okay, to m equal 1. This is the Lyman series, and it has the longest, okay, this is a scale, an energy scale, so the longest the arrow, the highest the energy, so the higher the frequency, the smaller the wavelength, okay, so this is UV, okay, UV. Balmer, okay, it is for m equal 2, okay, so you have n equal 3, 4, blah, blah, blah. And so this is visible, okay, and infrared, okay. And here you have passion, which is infrared, okay. Okay, and if you put all of them on the same, okay, on the same spectrum here, so you have the wavelength in nanometers, so you have the smaller wavelength, okay, Lyman series, okay, higher energies, okay, this one, smaller wavelength, and passion, which are the highest 1000, 2000 nanometers, okay, nanometers, so it means that it is infrared, okay, visible, and this is UV. Okay, so I will stop here now.